Hi guys, in the last lecture what we covered is we saw what are the various kind of losses in a transformer. So what kind of losses we saw? First we saw the copper loss. We saw that copper loss was I1 square R01 and I2 square R02. Then we saw iron loss. Iron loss had two component, hysteresis loss, which was equal to eta Bm raised to the power x F into V. Next was eddy current loss, which was Ke Bm square F square T square, where T is the thickness of lamination and in hysteresis loss V is the volume of the core. Then we saw stray load losses. These losses occur in iron parts of the transformer and the conductors. These are just like eddy current losses but are induced due to the leakage flux, which depends on the current carried by the winding. Hence these are variable losses. And last we saw dielectric losses, which occur in insulating parts like insulation in the winding and oil of the transformer. They occur due to finite conductivity of the insulator. Okay. In this lecture we will see how to judge the performance of a transformer, what are the indices that we use to judge whether the performance is good or bad. So the first index that we use is called as efficiency. Efficiency in general terms means how well the transformer can convert the input power to the output power. Okay. Efficiency even in real life means how well we are working. Okay. Means what is my throughput. So efficiency is defined as simply output power by input power into 100. That is what fraction of input power transformer can convert to the output power. Now by energy conservation what I can write is input minus loss will be equal to output. So efficiency can be written as P in minus P loss by P in into 100, or otherwise we can write it as P out by P out plus loss into 100%. Okay, this will be my efficiency for any machine. Okay, for any machine efficiency will be defined like this. Now we need to find what specifically is the expression for the efficiency when it comes to transformer. So let us consider that transformer is loaded to the x% of the rated load or full load. Suppose the transformer is loaded to x% or let us say in fraction x times of full load. X is the fraction of the full load. Let us say if 10% of full load means x is equal to 0.1. Okay. That means output power will be x into full load power. Loaded at x fraction of the full load means the output power will be x times the full load power, where x will be less than 1. Okay. Now full load power can be written as KVA rating of the machine into power factor. We know power is equal to S cos phi. Real power is equal to apparent power into cos phi. So what I have written is x into KVA rating into cos phi. Full load power will be rated apparent power multiplied by the power factor. Okay. Similarly, we saw that copper loss at x fraction of the full load is equal to x square P copper full load, and iron losses can be considered as constant. Usually these two type of losses I will consider. I will neglect any stray load loss and the dielectric loss. So what I can write efficiency as x kVA cos phi divided by output x kVA cos phi plus loss, that is iron loss, plus copper loss x square PCU full load into 100%. This will be my efficiency, that is output divided by output plus loss. Now, in any transformer, in any machine, my objective is to maximize the efficiency. That is, I want as much as possible, I want the input power to be converted to the output power. Okay? That means less power should be wasted and more power should be transferred from input to output. Just now we saw that efficiency depends on two factors, x and phi. Phi is the power factor angle. So if we want to maximize the efficiency, we can maximize it with respect to x or with respect to phi. So let us first maximize with respect to phi. Eta was written as x kVA cos phi by x kVA cos phi plus pi plus x square PCU FL. Now, if we differentiate with respect to phi using the quotient rule, it will be x into kVA minus sin phi, then x kVA cos phi plus pi plus x square PCU FL. Then differentiate the denominator, keep the numerator as it is, minus x kVA cos phi minus x kVA sin phi. This should be 0. Now these two terms will get cancelled out. Okay, because it is x square kVA sin phi cos phi. So what I am left with is x into kVA sin phi pi plus x square PCU FL equal to 0. So from this expression I can say sin phi is equal to 0 or phi is equal to 0. That is cos phi equal to 1. So maximum efficiency occurs at the unity power factor load. Okay. When we are varying the power factor, the maximum efficiency will be observed at unity power factor load. Next, let us try to maximize the efficiency with respect to x. Eta is x kVA cos phi by x kVA cos phi plus pi plus x square PCU FL. Now if we differentiate efficiency with respect to x, it will be kVA cos phi into x kVA cos phi plus pi plus x square PCU FL minus, if we differentiate the denominator, it will be kVA cos phi plus 2x PCU FL multiplied by x kVA cos phi should be equal to 0. For maximum efficiency, this should be equal to 0. So this term gets cancelled out. What I am left with is, we will be left with kVA cos phi pi plus kVA cos phi x square PCU FL minus 2x square PCU FL kVA cos phi. We can take out kVA cos phi common and then we can write down what we can write down is that pi, this term will be minus x square PCU FL equal to 0. So x will be under root pi by PCU FL. that is at this fraction of the full load, which is equal to under root pi by PCUFL, your efficiency will be maximum if you load the transformer to this much load. So this is the condition for maximum efficiency at this loading. Pi is equal to x square PCU full load. It is equal to PCU. That is constant loss will be equal to variable loss, or we can say iron loss is equal to copper loss. Whenever both the losses are equal, we will get the maximum efficiency. Next term is defined as all day efficiency. Now what happens? In distribution transformer, as I told you, the load is varying throughout the day. Sometimes we may be switching on the tube light, we may be switching on fan, sometimes we may not. Okay. So efficiency will also vary throughout the day as the output power is keeping on varying. So to determine the efficiency is not very good thing. Why? Because at every instant we need to determine a new efficiency. As the load changes throughout the day, we will be keeping on calculating the efficiency, and that will not carry much physical significance. So for distribution transformer, it is always better to calculate the all day efficiency. That is, we must calculate the efficiency at the end of the day for the entire day. So how to calculate that? All day efficiency is given as energy output by energy input into 100%. We will calculate the energy that is output of the transformer for the 24 hours and energy that has been taken as input by the transformer for the 24 hours. The ratio of two energy will give me the entire day efficiency. This is significant for distribution transformer where the load varies throughout the day, because when we are calculating the efficiency, it is at an instant, and that will not be physically significant when it comes to distribution transformer. But for power transformer, loading is constant at full load, so there we can calculate the efficiency instead of all day efficiency. Okay, this is for distribution transformer. Okay, for power transformer we do not calculate all day efficiency. Next, let us see what is the voltage drop in case of transformer secondary winding. Now suppose if we draw the model of the secondary winding, it will have a resistance and a inductance. Then there will be some load, let us say ZL. Here let us say the voltage is V1 dash, and this voltage will be, let us say, V2 dash. Okay. Now this is the equivalent resistance and reactance referred to the secondary, R02 and X02. Current flowing is I2. I need to find what is the voltage difference between V1 and V2. Okay. V1 dash is actually K times V1. That is by the transformation ratio. I need to find the voltage difference between V1 dash and V2 dash. Okay. So let us draw the phasor diagram of this transformer. So if we take V2 as the reference phasor or V2 dash, then we consider a lagging current, lagging this voltage by a power factor angle phi 2. Then V1 dash is equal to V2 plus I2R2 plus JI2 X2. I2R2 is like this, then JI2 X2 is like this. Okay, R2, or we can say R02. Then this will be my V1 dash. Okay, this will be the phasor diagram for the lagging load. Now I need to approximate the voltage drop between V1 dash and V2 dash. So let me draw this phasor again here. This was my current. This is I2R2, JI2X2. This is my V1 dash. Now let us mark some points to calculate the voltage difference. Let me draw this line like this horizontally. Now what to do is, take this much radius in the compass and rotate it so that this line lies along this. This will also be V1 dash. I have made an arc of this much radius. Now take this distance, this, then this, and then this distance. Okay, right now I am marking it as O, A, B, C, D. Now we can see V1 dash is equal to OD and V2 dash is equal to OA. So we need to calculate the difference between OD and OA. OD can be written as OA plus AB plus BC. Okay. So now if you see, this angle was phi, so this angle will also be phi, and this angle will also be phi. Now this length is I2R2, so AB can be written as I2R2 cos of phi, because we are finding the base of the triangle from the hypotenuse. Then BC can be written as I2x2 sin of phi from this triangle, and I am neglecting the term CD here. CD we are neglecting. Okay, so what I can say is OD minus OA is equal to AB plus BC, which is equal to I2 into R02 cos phi plus X02 sin phi. This is the voltage drop in the secondary winding of the transformer. Okay, this expression we have derived for a lagging load. If we take a leading load, then V1 dash minus V2 dash can be written as I2 R02 cos phi minus X02 sin phi. Okay, this expression will come if we take a leading load. So leading load has a minus sign and lagging load has a plus sign. That is the voltage drop in case of transformer from the induced EMF to the terminal voltage. Okay, this we have approximated. So this is an approximate expression, not the exact formula. Now next index that we define for measuring the transformer performance is voltage regulation. What is voltage regulation? Voltage regulation basically denotes the voltage fluctuation. Okay. Sometimes what you might have observed is, if we switch on too many things or too many devices at a home at the same time, then the voltage goes down. Okay, suddenly the voltage dips. That means the voltage is showing fluctuation. That is why with many devices we use stabilizer in our homes to maintain the voltage constant so that those devices are not damaged. You might have seen stabilizers with refrigerators and the air conditioners. Okay, why we use stabilizers? Because those are expensive devices and they should not observe the voltage fluctuation, otherwise they may get damaged. So voltage fluctuation is given by voltage regulation. Now as we increase the load on the system or as we draw more current from the system, the voltage will go down. Okay, so I want to know how much voltage can go down. That is why we define the voltage regulation. Voltage regulation has been defined in two types: regulation up, which is no load voltage minus full load voltage by full load voltage. Okay, that is, I want to measure the regulation between or fluctuation between when there is not any load on the system and when we have applied the rated load or the entire load on this system, because that will give me the maximum fluctuation or the maximum regulation. And we define a regulation down as V no load minus V full load by V no load. Okay, that is how we define the voltage regulation. If nothing is mentioned, most of the times we will be using regulation down. Okay, but it depends from problem to problem. Both the expressions for regulation are purely valid. Nothing is wrong. So even in case of examination, you must find out by both the expression to see which option is matching. Okay, At any point it will never happen that both the options will match, because only one type of regulation can be calculated, but both are entirely valid for each and every system. Now, if we see the model that we drew, it was something like this. Okay. Now suppose under no load condition there will be no current flowing in the transformer. So no load voltage here, if we see, if no current is flowing, V2 dash will be equal to V1 dash. So we can say no load voltage is V1 dash and full load voltage will be V2 dash. So what we can write down as regulation? Regulation will be V1 dash minus V2 dash by V2 dash. This will be regulation down, and regulation up will be V1 dash minus V2 dash by V1 dash. This is how we can define the voltage regulation for any transformer. Just now we calculated the voltage difference between V1 dash and V2 dash. So if we wish to write down voltage regulation in that terms, what I can write down is that voltage regulation would be I2 R02 cos phi plus X02 sin phi divided by V1 dash. This will be my regulation, and it can further be simplified as I2 R02 by V1 dash cos phi plus I2 X02 by V1 dash sin phi. Now I2 R02 is actually the voltage drop across the resistance divided by V1 dash. It is per unit voltage drop across resistance plus per unit voltage drop across reactance. So this is my voltage regulation, and you can multiply it by 100% to get in terms of percentage. Now as voltage regulation denotes the voltage fluctuation, what I want is the voltage regulation should be as low as possible, so that the voltage fluctuation between no load and the full load condition is pretty low. So we want the fluctuation to be less, that means the regulation should also be less. So let us derive a condition where we can determine what is the voltage regulation, least value and the maximum value. So voltage regulation is I2 into R02 cos phi plus X02 sin phi by V1 dash, or what we have seen other formula, epsilon R cos phi plus epsilon X sin phi, where epsilon R is per unit resistance voltage drop and epsilon X is per unit reactance voltage drop. Okay, that is how we define the regulation. So if we want to maximize the regulation, I will have to differentiate the voltage regulation with respect to phi. Okay, if we differentiate with respect to phi, it will be minus epsilon R sin phi plus epsilon X cos phi equal to 0. So it will be tan phi is equal to epsilon X by epsilon R, which is X02 by R02. Phi is equal to tan inverse X02 by R02. Okay, this will be my power factor angle for attaining the maximum regulation, and maximum regulation can only occur for lagging power factor load. This expression we have derived by using the regulation defined for lagging power factor. Okay, that is an undesirable condition actually, where the regulation is maximum. So this power factor is undesirable because here the regulation will be very high or voltage fluctuation will also be high. The desirable condition is that the voltage regulation should be 0. That is, no load and full load voltage are always equal. That means there is no fluctuation in the voltage as we increase the load. There should be no fluctuations in the voltage. So voltage regulation for leading power factor was epsilon R cos phi minus epsilon x sin phi. In lagging load, there is a plus sign between the two. In leading load, there is a minus sign between the two terms. Now, lagging load cannot have ever a zero voltage regulation because both the terms are in addition. So, it can never go to 0. So, for making the voltage regulation 0, we need a leading power factor load. If this is 0, then tan phi would be epsilon r by epsilon x. Phi would be tan inverse epsilon r by epsilon x. Okay. So, at this power factor leading, we will have the 0 voltage regulation. Okay. And above this angle, this term will dominate epsilon r cos phi and voltage regulation will be negative. Negative voltage regulation means no load voltage will be less than the full load voltage. That can only happen for leading power factor load. So, if we draw the curve of voltage regulation versus phi, this is phi, this is my voltage regulation. How will the curve look like? For lagging power factor load, the voltage regulation will always be positive. It passes through a maximum for an angle of tan inverse of x by r, x02 by r02. Then for leading power factor, it will go to 0 and then it will become negative. 0 it goes at tan inverse r02 by x02. At this angle, it will go to 0. This region is for lagging power factor. This region is for leading power factor. So, for leading power factor, mostly the voltage regulation is negative. Hence, you must always remember while solving a problem, if for a leading power factor you are getting a positive voltage regulation, please recheck your answers because it may be incorrect. Because practically for leading power factor, we get most of the times negative voltage regulation. So, let us summarize what we have covered in this lecture. We saw the two performance indices. First one was efficiency. We saw efficiency was equal to x kVA cos phi divided by x kVA cos phi plus pi plus x square PCU full load. And we saw efficiency is maximum at x is equal to under root pi by PCU FL or cos phi is equal to 1, that is unity power factor load. Then we saw voltage regulation. We saw voltage regulation is equal to I2 R02 cos phi plus X02 sin phi by V1 dash. This is for lagging load. And voltage regulation is equal to I2 into R02 cos phi minus X02 sin phi by V1 dash for leading power factor load. Voltage regulation is maximum at a power factor angle of tan inverse X02 by R02 and voltage regulation is 0 for a leading power factor angle tan inverse R02 by X02. Leading, lagging. Okay. So, this is what we have covered in this lecture. In the next lecture, we will see what are the various ratings that are associated with a transformer and how do those ratings vary.